Hello everyone. I decided it might be a good idea to actually have a video version of the sample problem that I was trying to cover at the end of class today, just because these types of titration calculations can be repetitive and they can also be a bit lengthy. And so this way you have a version of the problem that you can refer back to in case you need to sort of refresh your memory as to how to handle the different steps within a titration. If you recall, basically in class we were discussing how if I were titrating 25 milliliters of 0.16 molar acetic acid with 0.12 molar sodium hydroxide, what I would need to do to actually calculate the pH after several volumes of the base titrant had been added. And so if you recall, basically we said that if I were working with the solution of 0.16 molar acetic acid, and I hadn't added any base yet, then basically the pH of the system would depend entirely on the acetic acid on its own. And so I would consider the partial dissociation of acetic acid, and I would do the ice table that we've been working on over the past couple of chapters. The initial concentration would be 0.16 molar. And I wouldn't have any acetate or hydrogen ion initially. I would be losing some of the acetic acid, but gaining some of the acetate and some of the protons. And so my equilibrium concentration expressions would be as follows. I would then insert that into my expression for Ka, which would be the acetate ion times the proton concentration divided by the concentration of the acetic acid. That would give me the following polynomial equal to 1.8 times 10 to the negative fifth. And so again, it's at this point that we invoke the assumption that x is small. And if I go ahead and do the math that follows, I would get that x is equal to 1.7 times 10 to the negative third molar. I'll leave it to you to verify by doing the percent ionization calculation, but the percent ionization in this case worked out to be 1.1%, so that means that our assumption is valid. Okay, and if I'm going to calculate the pH, it would just be the negative log of the hydrogen ion concentration, and if this x is a valid x, then that would represent the hydrogen ion concentration, so my pH would be the negative log of 1.7 times 10 to the negative third, which, if you recall, in class we were able to figure out that that comes out to a pH of 2.77. Now, if I add 20 milliliters of base, then basically what's going to happen is I'm going to have to consider the neutralization reaction between acetic acid and sodium hydroxide. Now that would go fully to actually give me sodium acetate and water. And so I'm going to need to figure out which reagents are fully consumed, if any reagents remain, and if so, which one remains and by how much. In other words, I'd have to do a limiting reactant problem. In order to figure that out, I'm going to need to calculate how many moles of the acetic acid I have compared to how many moles of the base I just added. So again, you would have to multiply your volume of acid by your molarity of acid. So that would be, if I convert the volume to liters, I would have to convert that molarity of the acid to moles, and this came out to 4 times 10 to the negative third moles of the acid. Okay, and then I would do the same for the base. Okay, so 20 milliliters of base added at a concentration of 0.12 molar. That would mean that I added 2.4 times 10 to the negative third moles of the sodium hydroxide. Now, because the stoichiometry of the neutralization reaction is all 1-to-1, then if I subtract these two numbers of moles, then I'll end up with the number of moles of acid that remain, because if you notice, the limiting reactant in this case would actually be the base. So if I go ahead and do that calculation, I actually end up with 1.6 times 10 to the negative third moles of the acid remaining. Now, again, what I'm looking to do is eventually take this in to an ice table similar to the one that I used in the previous part of the problem. And so I'm going to need this to be a molar concentration. So I would divide through by the total volume of solution. In this case, if I had 25 milliliters of acid and I added 20 milliliters of base, that would give me 45 milliliters of total solution volume. If I divide that through, then basically I end up with a molarity of 0.036 molar acid. Now, the other thing to keep in mind is not only do I have 0.036 molar acid, and actually looking at our notes from class today, actually there was a little bit of a mistake here on the board. Essentially, not only will I end up with this much acid, but also I'm forming sodium acetate, which is a source of acetate. And the amount of acetate that forms corresponds to this number of moles, because basically the reaction stops after 2.4 times 10 to the negative third moles of sodium hydroxide are consumed. And since, again, the reaction stoichiometry is 1-to-1, then that means I also form 2.4 times 10 to the negative third moles of the acetate ion. And again, I'd have to convert that to a molar concentration, so I'd have to divide through by the total volume of solution. And if I do that, I actually end up getting a molarity of 0.053 molar in that acetate ion. So I'd have to use that as my initial concentration for the acetate instead of 0. And then I wouldn't have any protons yet. And then if I carry through with my ice table, then I'd still be losing some of the acetic acid, but gaining some of the acetate and also some of the protons. So if I work out the equilibrium concentration expressions, I would get the following. Okay, and so if I go ahead and work out that math, plugging this into our expression for the equilibrium constant, or the dissociation constant for acetic acid, I get this over 0.036 minus x, and that's going to equal 1.8 times 10 to the negative fifth. And again, I make my assumption that x is small, so that gives us the following math to solve. And an x value that ends up being 1.2 times 10 to the negative fifth molar. All right, now again, I'll leave you to check the percent ionization. But if you calculate the percent ionization in this case, you get 0.033%, so still well within our limits where we consider this a valid assumption. And if I calculate the pH in that instance would then be the negative log of 1.2 times 10 to the negative fifth. And so I end up with a pH here of 4.92. Okay, now, what happens after 33.3 milliliters of base have been added? Well, what would happen here is, if I go ahead and do the calculations, I already have my calculation of the initial amount of acid present. Okay, so I'm going to be reusing this in the parts that follow. But I still need to calculate how many moles of base I would have added if I added 33.3 milliliters of base at 0.12 molar concentration of base. And if I do this math, I see that I have 4.0 times 10 to the negative 3 moles of base added. All right, notice that that number of moles is the same as the initial amount of acid. And so basically, this point where I've added equal numbers of moles of acid and base, that would represent the equivalence point of the titration. Now, for a strong acid, strong base titration, if you recall, the pH at the equivalence point is 7. But since this is a weak acid, strong base titration, we're not going to get that same pH value. Since the acid was weak and the base is strong, I should be expecting a pH that is higher than 7 at the equivalence point. And so the way to figure that out is once again to consider the neutralization chemistry first before doing my ice table. Okay, and to sort of streamline the bookkeeping a little bit, I'm actually going to put together a table that's similar to an ice table for this neutralization reaction using the amounts in moles. Now, if you saw, I had initially 4.0 times 10 to the negative third moles of the acid and 4.0 times 10 to the negative third moles of the base with none of the acetate yet and none of the water. Since the neutralization proceeds 100%, then basically I'm going to lose 4 times 10 to the negative third mole on the product side, but gain 4.0 times 10 to the negative third mole of acetate and water on the product side. So that at the end of the neutralization reaction, I end up getting 0 moles each of the acetic acid and the sodium hydroxide, but I have 4.0 times 10 to the negative third moles of the acetate. Now, again, that means I'm going to need a concentration since eventually I will take this into an ice table. And so I'd have to divide by my total volume of solution, which would be 0.025 liters added to 0.0333 liters. And so that ends up being 0.0583 liters of solution, or total volume 58.3 milliliters. If I do that math, then basically that means I'm 0.069 molar in the acetate. So if all I have present is the acetate ion, now I have to consider the behavior of the acetate ion in solution. And acetate is the conjugate base of acetic acid. So I should be looking at its base behavior. And so if I do that, then I'm going to go and consider this equilibrium expression where now I need the Kb of the acetate ion. And so I'm going to go and drop in my initial concentrations. Initially, I would be 0.069 molar, of the acetate ion with none of the acetic acid and none of the hydroxide ion left. And then I'm going to lose some of that acetate ion but gain the species on the product side. I'd end up with 0.069 minus X as my equilibrium concentration of the acetate, but concentrations of X for the acetate and the hydroxide ion. Now, I'm going to need to plug this in. All right, so this would be, again, plugging into my expression of Kb. That would be X squared over 0.069 minus X. And this has to equal my value of Kb. But remember that Kb is going to be Kw divided by Ka, which would be 1.0 times 10 to the negative 14th, divided by Ka for acetic acid, which was given in the problem as 1.8 times 10 to the negative 5th. If I do that math, I would be setting this equal to 5.6 times 10 to the negative 10th. And so, again, making our assumption that X is small, then I would get X squared over 0.069. So again, assuming small x, that's 5.6 times 10 to the negative 10. If I solve, then X ends up being 6.2 times 10 to the negative 6 molar. Again, calculating out the percent ionization for this step just to check that our assumption is valid, I end up with 0.009%. I'll leave you to check that. But essentially that means our assumption is valid. And this would now represent my hydroxide ion concentration instead of my hydrogen ion concentration. Which means if I'm going to find the pH, then I need to, assuming 25 degrees Celsius is our system temperature, that would be 14 plus the log of the hydroxide ion concentration. So that would be 14 plus the log of 5.6 times 10 to the negative 10th. And so if I go ahead and calculate that out, my pH ends up being 8.79 for this particular step of the titration. What about after 37 milliliters have been added to the initial solution of the acetic acid? Well, here we're past the equivalence point. Okay, that means that we're going to have an excess of base. So that means that it's the base concentration that's going to be responsible for the pH that we actually end up experiencing. So let's calculate the new concentration of base. And so, as we've been doing in all of the previous parts of this problem, we're going to have to calculate the number of moles of base added and compare that to the initial number of moles of the acetic acid. And so if I go ahead and place my reaction equation in this section of the workspace, and if I go ahead and enter the initial number of moles of the acetic acid, all I need is to calculate the number of moles of the sodium hydroxide added. And so I would need to multiply the 37 milliliters converted to liters of the 0.12 molar sodium hydroxide. And if I go ahead and do that math, I end up with 4.44 times 10 to the negative third. And so if I go ahead and put that in, so this would be my number of moles of sodium hydroxide added. If I go ahead and put that in, so 4.44 times 10 to the negative third, all right, that means that the acetic acid is still the limiting reagent. I would subtract out 4 times 10 to the negative third moles of the acetic acid, and eventually I'd end up with 0 moles of acetic acid. If I go ahead and subtract that amount from the sodium hydroxide, then I end up with a quantity of 4.4 times 10 to the negative fourth moles of sodium hydroxide. Now, as we discussed in class today, initially I don't have any of the sodium acetate or the water. Technically I do form some of the sodium acetate, however, because the sodium hydroxide is a strong base and it dissociates completely, while the acetate ion is actually a much weaker conjugate base of the acetic acid, the amount of hydroxide ion that we would get from the acetate would actually be negligible compared to the amount of hydroxide that we get from the sodium hydroxide. And so that would mean that I can base the calculation of the pH of the system primarily off of, or actually solely off of, the moles of sodium hydroxide. And so if I go ahead and divide this through by the total volume of solution, so again that would be the 0.037 liters, all right, added to the initial 25 milliliters of the acetic acid, then that would mean I would have to divide through by 0.062 liters. And if I go ahead and do that math, I end up with 7.1 times 10 to the negative third molar. So that's my concentration of my sodium hydroxide. And again, because this is a soluble salt, and it's a 1-to-1 dissociation, and it's dissociation stoichiometry, then basically that's also the concentration of the hydroxide ion. So if I'm going to calculate the pH of the system, then that would be 14 plus the log of the hydroxide ion concentration. And so that would be 14 plus the log of 7.1 times 10 to the negative third. And if I do that math, then I get a pH of 11.85 if I do that calculation. Okay, so again, we've already discussed this example in class. We're going to also actually speak a little bit about titration curves in general, the different regions of titration curves. We'll be doing that with the reinforcement exercises that I posted on Google Classroom. So go ahead and give those exercises a try, and then we'll reconvene tomorrow in class and finish discussing this topic. All right, so again, as usual, if there are any questions, email, or if not, then by all means, bring up questions in class. All right, have a good night.